right, we're going to learn about the quotient rule for taking the derivative. We're going to find the derivative of tangent and cotangent, and also briefly mention secant and cosecant. And then we're also going to learn about something called higher order derivatives. So a lot to do. Going to go ahead and get started. There's a similar rule for a function that are in the form of quotients. When I say there's a similar rule, I mean similar to what we looked at for a product rule. So when we talk about quotients, we mean functions that are written with division, rational functions if we're taking a ratio of two things and comparing. So if the original function y is equal to f of x divided by g of x, then the change in y over the change in x, which would be the derivative of y with respect to x, is going to be equal to the lower function times the derivative of the higher function minus the higher function times the derivative of the lower function all over the lower function squared. So this version, y equals high over ho, then y prime equals ho d high minus high d ho over ho ho, which has a little bit of high ho in terms of the seven dwarfs. I also do if y equals high over low, then y prime equals low d high minus high d low over low low. And this one goes along with the same idea, except it's just high and low to remember top and bottom function. So low d high minus high d low over low low is what you will often hear me say in class. Officially, it's g times f prime minus f times g prime all over g of x squared. So let's go through and just do some sample problems applying a formula. For each of the following problems, find dy dx, which means find y prime, which means find the derivative. So in this situation, I have a function y that is defined with division. So I'm going to think about x to the fifth plus 7 being my lower function and 2x to the third being my higher function, which means that y prime is going to be equal to low d high minus high d low all over low low, or low squared. And that's it. Leave your answer. It's a mess, but you have found y prime. You have completed your task. It's done. It's over. You could use algebra to clean stuff up if you wanted to. You can multiply these things together and then multiply these things together and then combine like terms and do a whole bunch of stuff. But we're not going to. Okay, great. Example 2. I have a function that is defined with division. I'm going to count this as my low function, this as my high function. So my y prime is going to be equal to low d high, technically minus 0, but not going to write it, low d high minus high d low all over low squared. Just a reminder, low squared could be written as cosine of x quantity squared. Could be written how I wrote it in this problem. Do not write it like this. Not the same. Order of operations concerns. Don't do it. Example 3. I have a function y that is a division problem. I'm going to do my low and my high. So y prime is going to be equal to low d high minus high d low all over low squared. And again, you could distribute stuff together. You could combine like terms. You could make this such a beautiful, nice, rational answer. But we don't have to. We were just asked to find y prime. And I did it. And it's done. Example 4 and example 5, we're going to take a little bit of proving. So y equals tangent and y equals cotangent. You might be like, how and why are these on our quotient rule day? Well, because I don't know the derivative of tangent, but I do know that I could rewrite tangent as sine of x over cosine of x. In which case, using my new rule, y prime is going to be equal to low d high minus high d low. Oh no, my negative sign is not going to fit. Time out. Magic of a smart notebook. Let's move all of this over. There we go. So low d high minus high, the derivative of cosine is negative sine. So there's my d low. All over low squared. Well, lucky for me, I remember my trig identities. I've got cosine squared, double minus makes a plus, so plus sine squared, all over cosine squared. Sine squared plus cosine squared goes to 1. I have 1 over cosine squared of x, which is in fact secant squared x. So the derivative of tangent is equal to secant squared x. I'm going to ask you to pause your video and try to derive the same, but for cotangent. So I'll get you started and say we want to label y as cosine of x over sine of x. See if you can do something similar and get me a formula for y prime if y was cotangent. Pause your video, try now. All right, so I did the same thing, low d high minus high d low over low low. This time I had both of these were negative, so I factored out a negative sign. So then this thing goes to 1. I end up with y prime is equal to negative cosecant squared. So we've now proven 4 of the 6 trig derivatives. If you've got room on your paper, remind yourself that the derivative of sine of x, so if this is y, then y prime was cosine of x. Then we derived the derivative of cosine of x was equal to negative sine of x. Then we just learned that the derivative of tangent of x will be equal to secant squared of x, and the derivative of cotangent of x will be negative cosecant squared x. And then I'm going to give you a spoiler. The derivative of secant of x will be secant of x times tangent of x. You can prove that pretty quickly using the quotient rule and some trig identities. I'm not going to for the sake of time. Cosecant of x becomes negative cosecant of x times cotangent of x. And we'll talk a lot more about these 6 together, but just notice which ones have negative signs on them. Okay, again, the idea here being, the reason why we had a whole video that was dedicated to just these is if you know those, you can derive all of these. All right, last thing, higher order derivatives. We've learned the power rule, we've learned the product rule, we've learned the quotient rule, we've learned our trig derivatives. Now we can do all of that using multiple rounds. So a second derivative is just the derivative of the first, and the third derivative is the derivative of the second. This will especially connect us with physics. If you think of position being the original function, velocity is the first derivative, acceleration is the second derivative, because it's the rate of change of the rate of change. And then there's something called the jerk, which is actually the third derivative of position. It's the rate of change of acceleration. All right, so yeah, it's a lot. And the world is changing forever and always around us. Calculus models the world in rates of change. The notation for higher derivatives is similar, but pay close attention to a few things. So if I ask you to find the first derivative, that means find y prime. But if I'm using y prime notation, then the second derivative becomes y double prime, and the third derivative becomes y triple prime. Here's another version of prime notation. F prime is the first derivative, f double prime is the second derivative, f triple prime, which can be written in either one of these, represents the third derivative. Here's where things start to look weird. Normally, the first derivative, right, to do the derivative is d dx. That means take the derivative. Do it. This then is the first derivative. It's the change in y over the change in x. This notation then is the second derivative. This one is the third derivative. Because what's happening, if I started with, well, no, let's go way back. Let's go way back. If I had a function y and I said, hey, you, take the derivative of that y, you would say, well, it's the change in y over the change in x. But now I'm going to say, hey, do that again. Look in the numerator. I've got d squared y, and on the bottom, I've got dx. Technically, it's the quantity squared, but mathematicians are a little lazy. So we keep it just as dx squared. It was with respect to x twice. Then this one right here says, wait, hey, do that again. Take the derivative with respect to x. Well, now I've got the third derivative of y with respect to x. Okay, so it's all there. It does make sense. Just please note that it's not squaring the derivative. We're not going to be squaring our derivative with Leibniz notation. At least not anytime soon. Take the derivative with respect to f of x, right? This is a first derivative. This would say take the second derivative. This would take the third derivative. This is also some kind of funky notation that you'll see every now and again when you start to look stuff up online, but not really necessary for us. The other way you might see things is that you are supposed to take the derivative with respect to x when x is equal to, let's say, 2. So this bar just basically means when x is equal to 2, and that will get into some calculator notation. All right, so find the first 4 derivatives, find the value of g triple prime of 1, and find the fourth derivative. I'm going to have you try number 1. You're going to take the derivative, and then take the derivative again, and then take the derivative one more time, and then finally the fourth derivative. Pause your video, see what you get for the fourth derivative of f. Pause now. All right, so power rule, straight on through. Something to note though is you started with x to the third, and when you took the fourth derivative, we got to 0. Because polynomial derivatives will run out, right? If you think about lowering the power and lowering the power and lowering the power, you're eventually going to get to x to the 0, which will then be 0. All right, find the value of g triple prime of 1. Well, before we can find g triple prime of 1, we should start by finding g triple prime of x. You don't want to plug 1 in yet, otherwise things get weird real quick. So g prime of x, g double prime of x, and g triple prime of x are what I'm looking for. Go ahead and pause your video, then we'll talk about g triple prime of 1. Pause now, try this problem. All right, so I found g triple prime of x to be 24x minus 6. What I wanted to find, though, was g triple prime of 1. So within my g triple prime of x, everywhere I see an x, I'm going to replace that x with 1. 24 minus 6, g triple prime at 1 is going to be equal to 18, which means the third derivative of g at 1 is 18. Last problem, find the fourth derivative. So we're looking for not y prime, not y double prime, not y triple prime, but y quadruple prime if y equals 1 over x squared. You rewrite using algebra first, means we should think about y as being x to the negative second, so we're in power format to be able to apply the power rule. Go ahead and pause your video, see if you can find the fourth derivative of this y. All right, rewriting this way so I can use the power rule leads me to y prime, double prime, triple prime, quadruple prime. This would be 100% an okay answer. This is just the answer cleaned up a little bit. So remember quotient rule, low d high minus high d low over low low. 6 trig derivatives have now been shown to you, and you can take the derivative of the derivative.